Welcome to the series on AI for quantum security.
This is not a claim that quantum computing is breaking modern encryption today. This is not a claim that this Nature paper reveals a hidden exploit. And this is not a speculative sci-fi discussion about distant future. The paper we're discussing is a capability review. It surveys how artificial intelligence is being used to make quantum systems more usable, more scalable, and more automated. From a research perspective, that's exciting. From a vendor perspective, it's commercially necessary, but from a security and compliance perspective, that capability acceleration is potential breach of duty machine. Whenever a technology reduces human bottlenecks, automates control over physical systems, concentrates knowledge into machine-learned artifacts, or lowers the barrier to sophisticated operations, it creates new attack surfaces and new legal obligations. That's the lens we're going to apply to all the episodes of the series to come. I'm Nupur Mitra, a legal and governance risk translator for AI systems. This is the quantum AI threat almost nobody's talking about. Follow the AI Law, my channel, for daily breakdowns starting January 12th, Monday 2026. So the central framing of this task is simple. The security risk is not quantum computing itself. The security risk is AI-enabled operationalization of quantum systems. Quantum hardware in a lab is relatively inert from a security standpoint. Quantum hardware controlled by ML-driven pipelines, exposed via cloud platforms, trained on sensitive telemetry, and developed through international collaboration is a very different thing. That shift from experimental physics to automated cyber-physical systems is exactly what this paper is describing. Our job today is to understand what assets they emerge when AI is embedded into quantum workflows, how those assets can be attacked or misused, what controls vendors must implement to remain secure, compliant, and credible. A common mistake is to think quantum is in production yet, so security can wait. That assumption is already false for three reasons. AI collapses timelines. AI doesn't just improve performance, it compresses development cycles. Tasks that used to take months of expert manual tuning now happen automatically and repeatedly. Security timelines track automation, not scientific milestones. 2. Data and models are valuable before hardware scales. You don't need a million-qubit machine to leak proprietary device, fingerprints, control heuristics, or decoder strategies. Those assets are valuable today to competitors, nation-state labs, and supply chain adversaries. And 3. Regulators don't wait for commercialization. Export controls, cybersecurity regulations, and contractual obligations apply during R&D, not after product launch. Many organizations discover this only after exposure occurs. So this is not a future quantum problem. It is a current AI plus data governance plus supply chain problem. This opening slide has 3 jobs. Define the scope. We are focusing on vendors and developers, not abstract research. Anchor the threat model. Capability acceleration creates risk. Set the mental model. Think cyber-physical systems, not just code. Everything that follows, threat actors, attack surfaces, compliance checklists, flows from this foundation. If you imagine a triangle at the center of the slide, the 3 corners are capability acceleration. AI reduces friction in calibration, compilation, decoding, and control. ML in the loop control. Machine learning systems don't just advise, they act on hardware. Sensitive and controlled data. Telemetry, device fingerprints, model weights, and control parameters are all high-value assets. Security risk emerges not from any one corner alone, but from their interaction. Remove AI and systems are slow but understandable. Remove sensitive data and models are less powerful. Remove automation and humans remain the gatekeepers. This paper is explicitly about bringing all of these 3 together. One of the most important things to understand here is that research papers do not use security language, even when they describe security relevant capabilities. For example, when the paper talks about learning device characteristics otherwise inaccessible to into experiments, a security professional hears latent information extraction and reverse engineering. When it discusses optimizing control voltages using ML, a security professional hears automated control plane decision making. When it describes AI decoders implemented on FPGAs, a security professional hears firmware integrity and silent correctness risk. So this paper isn't wrong, it's just speaking a different dialect. Our task as vendors is to translate capability into responsibility. This threat model applies most strongly to vendors and developers, not purely academic labs. Why? Because vendors store large volumes of telemetry and customer data, deploy ML models repeatedly and automatically, expose systems through APIs or cloud platforms, operate across borders, and are contractually accountable to customers. So in other words, vendors turn capability into infrastructure, and infrastructure is what attackers, regulators, and litigators care about. Another clarification. When we say security, we're not only talking about hacking, breaches, or malware. We're talking about 4 overlapping risk categories: confidentiality, integrity, availability, and safety and correctness. Confidentiality, trade secrets, customer circuits, device telemetry. Integrity, calibration correctness, decoder accuracy, model authenticity. Availability, uptime of scarce quantum resources, prevention of subtle denial of service attacks. Safety and correctness, preventing silent errors, ensuring experimental and customer results are trustworthy. So for quantum vendors, correctness is a security property. If results can be subtly biased or degraded without detection, trust collapses. This is just an introduction here today. We'll be detailing it later in the series. Even on this first slide, it's important to flag that legal exposure is inseparable from technical risk. This includes export controls and deemed export rules, trade secret law, contract and liability exposure, emerging cybersecurity regulations for digital products. Later slides will unpack these in detail. For now, understand this. Security failures in quantum systems are rarely just technical. They tend to escalate quickly into regulatory reporting obligations, customer disclosures, and reputational damage. So, having established the framing, here's how the rest of the presentation unfolds. We'll identify the crown jewels that emerge in AI for quantum systems. We'll map realistic threat actors to those assets. We'll walk through concrete threat scenarios, each directly derived from capabilities discussed in this paper. We'll then translate those threats into a practical compliance checklist that engineering, security, and legal teams can actually implement. Finally, in this series, we'll discuss how to operationalize this without slowing innovation. The goal is not fear. The goal is resilience with credibility. So this one sentence would frame everything that follows in the series. In quantum technology, the moment AI enters the control loop, security stops being optional research hygiene and becomes operational risk management. So with that framing in mind, let's move ahead and define exactly what assets are at stake. So here lies the question, why security and legal teams care about AI for quantum capabilities. So before we talk about threats, controls, or compliance, we need to answer a very basic but often misunderstood question. Why do security teams and legal teams, they care about this research at all? At a first glance, a paper titled Artificial Intelligence for Quantum Computing looks like a purely technical or academic discussion. There's no mention of cyber attacks, cryptography, breaches, or adversaries. And that's exactly why this conversation is necessary, because the absence of explicit security language does not mean the absence of security impact. What this slide does is explain why the capabilities described in the paper immediately trigger concern for security, legal, and compliance stakeholders, especially in a vendor or developer environment. So let's start with the most important mental shift. In engineering and research, we often treat new capabilities as neutral tools. In security and law, capability is never neutral. Every capability answers three implicit questions. Who can do something now they couldn't before? How quickly can they do it? With how much oversight? This paper is fundamentally about reducing friction, less manual calibration, less expert tuning, fewer human bottlenecks, faster iteration cycles. From a product and research standpoint, that's progress. But from a risk standpoint, that is attack surface expansion. Security teams care not because the paper is dangerous, but because it changes the shape and velocity of operations. It's important to separate two ideas that are often conflated. Quantum computing as a theoretical capability, AI-enabled quantum systems as an operational platform. Quantum computing by itself is slow to scale, expensive, and heavily human-mediated. AI changes that by introducing automation, generalization, and abstraction. This is the same pattern we've seen in every other domain. AI in finance, algorithmic trading risk. AI in aviation, autopilot and decision support risk. AI in manufacturing, cyber-physical sabotage risk. Quantum computing is following the same trajectory. The moment AI systems make decisions, tune parameters, generate executable artifacts, or close feedback loops, security and legal exposure, they increase dramatically. So let's walk through the types of things the paper discusses and how they map to security concerns without yet getting into specific threats. The paper repeatedly emphasizes that AI can perform tasks previously handled by scarce human experts: calibration, error mitigation, circuit optimization, control tuning. From a security standpoint, automation means decisions happen faster than human review. Mistakes propagate more widely. Malicious manipulation can scale. Security teams recognize this pattern immediately. This is the same risk class as automated trading systems, self-healing networks, autonomous control systems. A central claim in this paper is that AI can extract patterns from experimental quantum data that are difficult for humans to model, inaccessible to traditional analysis. This is scientifically powerful and legally sensitive. The security and legal teams here, this data encodes proprietary knowledge. This data may be controlled technical information. This data may enable reverse engineering. The more value that can be extracted from data, the more that data becomes a regulated asset. And theme 3, integration with real hardware. This is critical. The paper is not about simulations alone. It explicitly discusses real quantum devices, real quantum electronics, real error correction pipelines, real accelerators like GPUs and FPGAs. So once software directly influences hardware behavior, we have crossed into cyber-physical systems. Cyber-physical systems have different security properties. Errors can cause physical degradation. Subtle manipulation can go unnoticed. Availability losses are expensive and visible. Security teams are trained to be extremely cautious whenever software controls physical processes. So why this matters more for vendors than academics? At this point, someone often asks, isn't this just research? Why treat this like infrastructure? The answer is vendors operationalize research. Vendors store data long term. They deploy systems repeatedly, provide access to third parties, and are legally accountable for outcomes. A paper describing a calibration technique becomes a pipeline, an API, a customer-facing service, or a production workflow. And once that happens, the risk profile changes completely. One of the most subtle but important points in this paper is its focus on scaling. Not scaling in the sense of breaking cryptography, but scaling in the sense of managing more qubits, managing more experiments, managing more devices, managing more users. Scaling creates security problems because humans stop being gatekeepers. Manual review becomes impossible. Assumptions baked into early prototypes break. Security and legal teams know that scaling is where incidents happen, not at the prototype stage. From a legal perspective, 3 red flags appear immediately when reading this paper. 1. Concentration of trade secrets. If AI models learn device-specific behavior, then model weights, training data, and derived parameters may all qualify as trade secrets. Trade secret law doesn't care whether something is just data. It cares whether it derives value from secrecy and is subject to reasonable protection. This paper strongly implies both. 2. Export control implications. Quantum technology is already export controlled in many jurisdictions. AI-enhanced quantum workflows, they raise additional questions. Is telemetry controlled? Are trained models controlled? Is sharing access equivalent to exporting technology? Legal teams are trained to spot ambiguity because ambiguity is where enforcement actions live. 3rd, forcibility of harm. In liability law, forcibility matters. Once a capability is documented and understood, organizations can no longer claim we didn't know this could happen. So this paper establishes AI influences control, AI influences correctness, AI influences performance. That makes certain failure models foreseeable, which increases legal responsibility to mitigate them. A concept that sits at the intersection of security and law is dual use. Dual use doesn't mean malicious intent. It means a capability developed for benign purposes that can reasonably be repurposed for harmful ones. The paper describes dual-use capabilities: inference from data, optimization of controls, automation of complex decision-making. Security and compliance teams don't need proof of misuse. They need credible potential. That potential exists here. Some organizations react defensively. This will slow us down. We don't want to scare customers. This is just theoretical. In practice, the opposite is true. Ignoring security and legal implications creates brittle systems, reactive compliance, credibility gaps with customers, and higher costs when controls are added later. Organizations that address these issues early move faster with confidence, close enterprise deals more easily, and survive regulatory scrutiny. So if you need a board-level explanation, it is this. AI turns quantum research into operational infrastructure. Operational infrastructure must be governed. This is the same evolution seen in cloud computing, machine learning platforms, autonomous systems. Quantum is not special in this regard. It is simply earlier in the curve. So now that we have established why security and legal teams care, the next logical question is, what exactly are we trying to protect? So the next video in the series will identify the crown jewels, the assets that become valuable, sensitive, and regulated once AI for quantum systems are deployed. Those assets are the anchor for the entire threat model. If you work on AI, security, or law and want to understand what actually gets you sued and what should change, you are in the right place. Subscribe to my channel, The AI Law. See you in the next episode of the series. Before we talk seriously about threats, controls, or compliance, we have to answer a deceptively simple question. Who exactly are we talking about when we say quantum vendor or developer? This matters more than it sounds. Threat models fail most often not because the threats are misunderstood, but because the scope is fuzzy. People assume this doesn't apply to us, or that's someone else's problem. So this video is about drawing a clean boundary around who this threat model applies to, and just as importantly, who does not apply. So let's start by being precise. This scope is not a lone academic lab doing exploratory research with no external users. It is not a purely theoretical group running simulations only, or it is not a single prototype system operated by one trusted team. The scope is organizations that build, package, operate, or expose quantum technology or quantum enabling software. Organizations that store, process, or monetize quantum-related data or IP. And organizations that interface with customers, partners, or collaborators. So in other words, the moment quantum research becomes a product, a service, a platform, or a shared infrastructure, you are in scope. I'm Nupur Mitra, a legal and governance risk translator for AI systems. On my channel, The AI Law, I unpack how AI security flaws, governance failures, and model behavior turn into real legal exposure, rights issues, and the future of jurisprudence. This distinction is critical. Academic researchers are primarily concerned with correctness of results, novelty, and reproducibility. Vendors and developers must also care about confidentiality, integrity at scale, availability guarantees, legal obligations, and customer trust. The same technique that is harmful in a closed lab becomes risky when automated, exposed through APIs, or reused across multiple devices and customers. This paper describes techniques that vendors will inevitably operationalize. This slide defines what operationalize really means. For this threat model, we consider 5 overlapping categories. Many real organizations fall into more than one. These are organizations that design, fabricate, or operate superconducting qubit systems, trapped ion systems, photonic quantum processors, or hybrid architectures. So why they are in scope? They collect vast amounts of raw telemetry. Their devices have unique proprietary characteristics. Control and calibration directly affect physical systems. Their most valuable IP is often not the chip layout. It is the accumulated operational knowledge embedded in data and models. Category 2, control stack and firmware developers. This includes teams that build pulse-level control software, firmware for control electronics, real-time feedback systems, calibration pipelines. Why are they in scope? Their software directly controls hardware behavior. Errors or manipulation can degrade performance or damage systems. ML-driven automation increasingly lives here. This layer is a control plane. Control planes demand stronger integrity guarantees than ordinary application code. Category 3, quantum software platform providers. These are vendors offering compilers, circuit optimizers, SDKs, transpilers, or workflow orchestration tools. Why they are in scope? They transform user intent into executable operations. AI-generated or AI-optimized outputs may run directly on hardware. They often handle customer IP, circuits, algorithms. They sit in the supply chain between user and hardware. Supply chains are prime attack targets. Category 4, quantum cloud and service providers. This includes any organization that offers quantum access via cloud APIs, schedules jobs, manages multi-tenant environments, or brokers access to partner hardware. So why are they in scope? They aggregate customers, data, and execution environments. They must isolate tenants. They are legally accountable for uptime, correctness, and confidentiality. They are infrastructure providers even if the hardware is experimental. Category 5, AI for quantum tool developers. These are teams building ML-based calibration tools, AI decoders for error correction, generative models for circuits, optimization frameworks. Why are they in scope? Their models encode valuable system knowledge. Their artifacts are often reused across devices and customers. They blur the line between software and system behavior. Models become high-value assets and high-risk artifacts. A common objection at this point is, we don't sell this, it's internal tooling. That does not remove you from scope. Internal tools still affect system behavior, create records and artifacts, and influence outcomes customers rely on. So from a security and legal perspective, internal does not mean low risk. Internal often means less audited. Some of the most serious incidents in technology come from internal systems that were never threat modeled because they were not customer facing. Quantum development is highly collaborative. Vendors routinely work with universities, government labs, international partners, hardware suppliers, and customers doing joint research. This introduces cross-border data flows, shared infrastructure, mixed trust boundaries. From a threat model perspective, collaboration expands scope dramatically. Even if you're careful, your collaborators' practices can create exposure for you. Another subtle but important point. When we say developer, we include physicists, research engineers, data scientists, and ML researchers inside vendor organizations. Now you'll ask, why? Because from a risk standpoint, a researcher notebook, a training data set, or an experiment log, they can be just as sensitive as production code. Security and compliance controls must extend into research environments, not stop at the product boundary. To make this conversation concrete, it helps to visualize the quantum vendor stack as layers. Physical layer, qubits, cryogenics, optics, electronics. Control layer, firmware, pulses, timing, feedback loops. Data layer, telemetry, logs, experiment results. ML layer, training pipelines, models, decoders, optimizers. Application layer, compilers, SDKs, customer-facing APIs. And governance layer, access control, logging, compliance, and export restrictions. This threat model applies across all layers. Security failures often occur when responsibility between layers is unclear. Many organizations attempt to scope narrowly. Security owns cloud, engineering owns models, legal owns export controls. That fragmentation is dangerous. The risks described in the research paper as we are discussing emerge between layers. When ML outputs feed control systems, when telemetry feeds trading, and when collaboration feeds datasets. Threat modeling must therefore be cross-functional. To avoid confusion, let's be explicit about what is not covered here. Speculative future cryptanalysis by large-scale quantum computers. Consumer endpoint security. Unrelated AI ethics topics. Purely theoretical quantum algorithms with no operational footprint. Those are important, but they are not the focus of this threat model. This scope is about operational AI for quantum systems. One reason to be disciplined about scope is credibility. When regulators, auditors, or enterprise customers ask, a clear defensible scope shows maturity, prevents overclaiming, and avoids blind spots. So this video gives you the language to say, we have identified where our responsibilities begin and where it ends. So now that we have clearly defined who is in scope, what kinds of systems we are talking about, and why vendors and developers are uniquely exposed, the next question becomes unavoidable. What exactly are the assets within the scope that attackers, competitors, or regulators care about most? The next video will identify those crown jewels, the specific technical and legal assets that anchor the threat model. Everything else flows from that. If you work on AI, security, or law and want to understand what actually gets you sued and what would change, you are in the right place. Subscribe to my channel, The AI Law, and let's meet in the next episode of the series.
Welcome back to the series.
Before anyone can meaningfully talk about attackers, vulnerabilities, or controls, we have to answer one foundational question. What are we actually protecting? In security work, this is known as identifying the crown jewels, the assets where loss, manipulation, or exposure would cause outsized harm. This video is critical because quantum vendors often misidentify their most valuable assets. They assume it's source code, chip designs, or published algorithms. In reality, AI for quantum systems, they shift value away from static artifacts and toward dynamic, learned, and operational assets. If you protect the wrong things, you can spend millions on controls and still lose what matters most. Why AI changes what counts as a crown jewel? Traditionally, intellectual property was human-readable, documentable, and relatively static. AI breaks that model. In AI-enabled systems, value concentrates in data, learned representations, and execution context. Quantum systems amplify this effect because devices are highly individualized, performance is fragile, and small advantages they compound dramatically. So this video reframes what valuable means in this domain. I'm Nupur Mitra, a legal and governance risk translator for AI systems. On the AI law, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, rights issues, and the future of jurisprudence. High-level categorization of crown jewels. We'll group the crown jewels into two broad classes: technical assets and legal and business assets. Technical assets, things that directly affect system performance, correctness, or competitive advantage. Legal and business assets, on the other hand, things that create regulatory, contractual, or reputational exposure if mishandled. Both matter equally. Losing one often cascades into losing the other. Technical crown jewels. Asset 1. Raw experimental telemetry. Let's start with the most underestimated asset, raw telemetry. This includes readout traces, calibration sweeps, timing data, noise measurements, environmental signals, experiment logs. Why this is a crown jewel? Because telemetry is not just measurements. It is a record of how your system behaves in reality, not in theory. AI systems can extract from telemetry device-specific noise fingerprints, correlations humans don't notice, and latent parameters that define performance limits. From a competitive and security standpoint, this is extremely valuable. If an adversary obtains sufficient telemetry, they may not need your hardware designs at all. Asset 2. Derived device, fingerprints, and models. Closely related but distinct are derived representations, noise models, error models, device embeddings, learned representations of qubit behavior. These often live in trained ML models, configuration files, serialized parameters, or optimization heuristics. Why these are crown jewels? They encode months or years of operational learning. They are far easier to exfiltrate than hardware. They are difficult to reconstruct from publications alone. From a legal standpoint, these often qualify as trade secrets, even if the underlying physics is public. Asset 3. Control parameters and calibration outputs. Control parameters include voltage schedules, pulse shapes, timing offsets, feedback rules, calibration solutions. These may look mundane, but they're extremely sensitive. Why? Small changes can drastically alter performance. They often differ per device. They can reveal internal system structure. In AI-driven calibration systems, these parameters are often generated automatically, updated frequently, and deployed without human review. And that makes them both valuable and vulnerable. Asset 4. Error correction decoders and models. Quantum error correction decoders, especially AI-based ones, are a major crown jewel. They include model architectures, trained weights, inference pipelines, accelerator implementations. Why they matter? They directly affect logical error rates. They can be tuned to specific devices. They are hard to validate externally. A compromised decoder may silently degrade results, bias outcomes, or create subtle availability issues. From a trust perspective, this is one of the highest risk assets in the stack. Asset 5. FPGA and accelerator bit streams. When decoders or control logic are implemented on FPGAs, GPUs, or other accelerators, the bit streams and firmware, they all become crown jewels. Why? They are executable logic. They're opaque to most review. They sit below application level security controls. Tampering here is particularly dangerous because it can evade detection, it can persist across updates, and it can undermine correctness guarantees. Quantum compliers and optimizers, they often include mapping heuristics, scheduling strategies, hardware-aware optimizations. Even when the compiler is open source, the configuration and tuning are often proprietary. AI-assisted optimization further concentrates value. The how becomes learned rather than explicit, and behavior may differ subtly across devices. These artifacts, they determine performance, cost, and customer satisfaction. Asset 7. Customer circuits and workloads. Finally, never forget your customers' assets, they become your crown jewels. Customer circuits may represent proprietary algorithms, sensitive research, regulated workloads. Even if you don't understand the semantics, you're responsible for confidentiality, integrity, and non-tampering. Any threat model that ignores customer IP is incomplete. Now the next part, legal and business crown jewels. Asset 8. Trade secret status itself. Trade secrets only exist if information is secret. It derives value from secrecy, and reasonable steps are taken to protect it. Poor security controls, they can destroy trade secret protection even if no breach occurs. From a legal perspective, failure to protect can equal disclosure, and this makes security controls part of your IP strategy, not just IT hygiene. Asset 9. Controlled technical data. Export control. Certain quantum-related information may be subject to export controls, deemed export rules, national security regulations. This can include performance characteristics, control techniques, detailed telemetry, or advanced error correction methods. Once classified as controlled improper access, even internally, it can create legal exposure. Asset 10. Customer trust and contractual assurances. Many quantum vendors, they operate in government, defense, finance, or regulated research environments. Customers will ask, how do you protect our data? How do you ensure correctness? How do you prevent tampering? Failure here doesn't just risk breach, it also risks loss of market access. Asset 11. Regulatory posture and audit evidence. Increasingly, regulators and customers, they expect logs, provenance, access records, model lineage. The ability to prove what happened becomes a crown jewel itself. If you cannot demonstrate control, you may be treated as if you had none. So why crown jewels shift over time? One important nuance, crown jewels are not static. As AI systems evolve, Models may become more valuable than data. Automation may increase the blast radius of errors. Collaborations may expand exposure. And this is why crown jewel identification must be revisited regularly. Common failure modes at this stage. Organizations often fail here by focusing only on code, ignoring data and models, assuming internal assets are low risk, or underestimating legal implications. This video is designed to prevent that failure. Now that we've identified what matters most, the next step is to ask, who might want these assets and why? The next video introduces the threat actors most relevant to quantum vendors and developers and explains their motivations and capabilities. So understanding adversaries is essential before discussing controls. I'm Nupur Mitra, a legal and governance risk translator for AI systems. On the AI law, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, rights issues, and the future of jurisprudence. When people hear threat vector, they often picture a hoodie-wearing hacker who's trying to break into a system from the outside. That mental model is incomplete and dangerous, especially in the quantum vendor context. For AI for quantum systems, the most serious risks often come not from dramatic break-ins, but from well-resourced competitors, nation-state research ecosystems, trusted insiders, or ordinary collaboration patterns that quietly exceed legal or security boundaries. This video is about realistic adversaries and not sensational ones. I'm Nupur Mitra, a legal and governance risk translator for AI systems. On the AI law, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, rights issues, and the future of jurisprudence. So why threat actors must be explicit? Threat modeling fails when organizations say, we don't know who could attack us, or we're too early at stage to be a target. In reality, capability attracts attention, not revenue. Data attracts interest, not marketing. And asymmetry favors patient adversaries, not noisy ones. This research paper signals that AI for quantum capabilities are maturing, and that alone is enough to attract attention. Let's start with the most obvious but often misunderstood actor, nation-state laboratories. Nation-state laboratories and their proxies, they care deeply about quantum advantage, strategic parity, and long-term technological leverage. Important clarification here. This does not mean espionage movies or cloak and dagger theft. More often it means aggressive talent recruitment, participation in open collaborations, strategic partnerships, and targeted collection of non-obvious technical artifacts. From a threat model perspective, they have patience, they have expertise, and they understand exactly which data and models matter. They're particularly interested in telemetry that reveals device behavior, learned calibration techniques, and AI-enhanced error correction methods. Competitors are often underestimated as threat actors because their behavior is usually legal or at least ambiguous. Competitors want to reduce their own R&D timelines, to avoid dead ends, and to reproduce performance gains without equivalent investment. So they don't need to steal everything. They just need enough telemetry, enough model behavior, or enough insight into control strategies to close the gap. AI for quantum systems, they increase this risk because learned behavior is hard to document defensively, and exfiltration of models or data is easier than physical theft. Supply chain threats are especially relevant here because AI for quantum stacks, they depend on complex software ecosystems, accelerators like GPUs and FPGAs, firmware, drivers, and ML frameworks. A supply chain adversary doesn't need to attack you directly. They can just compromise a dependency, tamper with a firmware image, or insert malicious logic into a build process. The danger is not necessarily data exfiltration, but silent manipulation, altered decoder behavior, biased optimization, degraded performance that looks like noise. These attacks are hard to detect and devastating to trust. Insiders are one of the most important and uncomfortable categories. This includes employees, contractors, visiting researchers, interns, and collaborators with elevated access. Most insider risk is not malicious. It is oversharing, convenience-driven shortcuts, misunderstanding of sensitivity, or reuse of data or models across projects. AI for quantum environments are particularly vulnerable because data and models, they're often shared informally. Research culture, it encourages openness, and sensitivity is also not always clearly labeled. From a legal standpoint, intent often does not matter, the impact does. For organizations using shared cloud infrastructure, another actor appears. Co-tenants on shared hardware or users sharing logical infrastructure. Even without malicious intent, risks include side channel leakage, misconfigured storage, shared accelerator contention, logging, and metadata exposure. This is especially relevant for GPU-based ML training, shared FPGA pools, or multi-tenant quantum job platforms. Security here is about isolation and assurance, not just authentication. This is the most subtle category. Collaborators often include universities, joint research partners, customers doing co-development, government-funded consortia. These actors are trusted, but trust is not a security control. Risks arise when data crosses borders, access exceeds need to know, models are reused beyond original scope, or collaborators train derivative systems. From an expert control and IP standpoint, this is often where violations occur without malicious intent, mind you. A key insight for this domain: motivation, it matters more than technical skill. The actors described already understand quantum systems, they already understand machine learning, and they already know what data is valuable. They don't need to figure out your system. They need access, persistence, and plausible deniability. This is why perimeter-only defenses are insufficient. Across these categories, threat actors, they typically have domain expertise, long time horizons, ability to operate quietly, and interest in subtle degradation or inference, not dramatic failure. So this means attacks may not trigger alerts, losses may be gradual, and damage may only be discovered later, if at all. Another misconception: why would anyone target us before large-scale quantum advantage exists? Because early data and models, they shape future capability. Small advantages compound, and knowing what doesn't work is almost as valuable as knowing what does. This research paper makes it very clear that AI is being used to navigate a vast design space. Mapping that space is expensive, stealing that map is cheaper. Defenders must protect all crown jewels across all layers against multiple actor types. Attackers only need one misconfiguration, one overshared dataset, one unsigned model, or one careless collaboration. This asymmetry is why early threat modeling matters. At this stage, organizations we hear often say, we trust our people, we don't see ourselves as a target, our data isn't that valuable. These statements are rarely true in aggregate. Threat actors do not need you to see yourself as a target. They just need opportunity. Now that we understand what assets matter and who might want them, the next step is to ask, where concretely can these actors interact with our systems? The next episode introduces the attack surfaces, the technical and organizational touch points where risk becomes real. If you work on AI, security, or law and want to understand what actually gets you sued and what would change, you are in the right place. Subscribe to my channel, The AI Law, and see you in my next episode of the series. So now that we've identified what assets matter and who might want them, we can finally ask the most operational question in the entire threat model. Where can things actually go wrong? This video is about attack surfaces, the points where threat actors can interact with your systems intentionally or unintentionally and then cause harm. Importantly, attack surfaces are not always obvious. They often emerge from convenience, automation, and integration, rather than from exposed network ports. Traditional quantum research environments were relatively contained. Few users, manual workflows, ad hoc processes. AI for quantum systems changed this by introducing continuous data flows, automated pipelines, reusable models, and cross-team tooling. Every integration point is a potential attack surface, and this video, it maps those points explicitly. I'm Nupur Mitra, a legal and governance risk translator for AI systems. On the AI Law, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, rights issues, and the future of jurisprudence. Attack Surface 1. The first and often largest attack surface is data capture. This includes raw readout traces, calibration sweeps, error logs, experiment metadata. Why this surface is risky? Telemetry is high volume and frequently accessed. It is often shared for debugging or research. It may be stored long-term in centralized systems. And common weaknesses, they are overly permissive access, unclear data classification, lack of export logging, ad hoc sharing with collaborators. This surface is often exploited not through hacking but through oversharing. Attack Surface 2. Machine learning training pipelines are a convergence point for many risks. They include data ingestion, pre-processing, labeling or reward assignment, training jobs, evaluation and tuning. Threats here include data poisoning, subtle bias injection, leakage of training data, unauthorized reuse of datasets. Because training pipelines are often treated as internal, they may lack strong authentication, auditing, or change control. Yet, compromise here can influence every downstream model. Attack Surface 3. Once models are trained, they must be stored, versioned, and deployed. Model registries are a high-value target because they centralize powerful artifacts. They often lack the rigor applied to source code, and they may allow overrides or silent updates. Risks include model substitution, rollback attacks, deployment of unreviewed models. This is particularly dangerous when models directly influence hardware control or perform error correction. Attack Surface 4. The control plane is where software decisions become physical actions. This includes pushing calibration updates, modifying control parameters, scheduling experiments. Attackers here don't need to exfiltrate data. They can degrade performance, increase error rates, or create denial of service conditions. Because behavior changes may look like normal noise, detection is hard. Control planes, they demand higher integrity standards than typical application layers. Attack surface 5. Accelerators introduce deep, opaque attack surfaces. GPU drivers and runtimes, FPGA bit streams, firmware update mechanisms. These layers often run privileged code. They are poorly monitored and they are difficult to inspect. Compromise here can bias results, leak information via side channels, or persist across system resets. This is a classic supply chain risk area. Attack surface 6. Any interface exposed to customers, partners, or external tools is an attack surface. This includes job submission APIs, circuit upload endpoints, result retrieval systems. Risks include injection of malicious circuits, abuse of resource scheduling, metadata leakage. Even well-authenticated users may unintentionally cause harm if safeguards are missing. Attack surface 7. Collaboration is a major but underappreciated attack surface. This includes shared cloud buckets, file transfer systems, joint notebooks, shared repositories. Risks arise from unclear ownership, inconsistent security practices, cross-border access. Often, no single team owns these surfaces, making them hard to govern. Attack surface 8. Finally, people and processes are attack surfaces. Examples: onboarding and offboarding delays, informal data sharing, lack of training on data sensitivity, ambiguous responsibility between teams. In AI for quantum systems, where research culture values openness, this surface is particularly large. It's tempting to focus on vulnerabilities, unpatched systems, misconfigurations, bugs. But in this domain, structural attack surfaces are more dangerous than individual flaws. If data flows freely, models are trusted implicitly, control loops lack guardrails, then vulnerabilities will eventually be found or created accidentally. A critical point: automation increases blast radius. A mistake in one training data set, one model, or one deployment, it can propagate across multiple devices, multiple customers, multiple experiments. Attack surfaces that seem minor at small scale, they become catastrophic at large scale. From a legal and regulatory standpoint, organizations are expected to identify and manage foreseeable risks. Ignorance is not a defense. Documenting attack surfaces demonstrates due diligence, reasonable care, and proactive governance. This matters when responding to audits, incidents, or litigation. Now that we know who the threat actors are and where they can interact with our systems, the next step is to examine how attacks actually unfold. The next video walks through concrete threat scenarios, each directly derived from the attack surfaces we've just identified. These scenarios turn abstract risk into operational reality. If you work on AI, security, or law and want to understand what actually gets you sued and what should change, you are in the right place. Subscribe to my channel, The AI Law, and I'll see you in my next episode of the series. This channel analyzes AI security legal risk, AI liability in practice, and AI governance compliance risk. We look at how AI system design, architecture, and runtime controls, they create legal risk in AI systems, AI model vulnerabilities and compliance failures, AI runtime controls and legal exposure, and how AI tooling risk translates to law for developers, security engineers, and governance teams. Threat Scenario 1. ML-enabled reverse engineering of quantum devices. We're starting the threat scenarios with this one for a reason. Machine learning reverse engineering of quantum devices. It is one of the most plausible threats, one of the most misunderstood, and one of the most under-defended risks in AI for quantum systems. It doesn't require breaking into hardware, it doesn't require stealing schematics, and it doesn't require spectacular cyber intrusions. It requires only access to data. Data that many organizations already treat as low risk. At a high level, this threat looks like this. A threat actor gains access to quantum telemetry or experiment data. They apply machine learning techniques to infer latent properties of the device. They reconstruct device-specific behavior that was never explicitly documented. They use that inferred knowledge for competitive, strategic, or malicious purposes. What makes this scenario powerful is that nothing illegal or obviously malicious needs to happen for it to succeed. I'm Nupur Mitra, a legal and governance risk translator for AI systems. On the AI Law, my channel, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, rights issues, and the future of jurisprudence. Traditionally, reverse engineering required physical access, detailed schematics, or invasive measurement techniques. AI breaks that dependency. Modern machine learning systems can infer hidden parameters, extract structures from noisy data, and generalize from partial observations. The research paper explicitly notes that AI can learn device characteristics otherwise inaccessible to experiments. From a security standpoint, that sentence should ring alarm bells. It means data you thought was harmless can now reveal secrets you didn't realize it contained. Let's walk through how this threat unfolds in practice. Step 1. Data access. The attacker obtains raw telemetry, calibration traces, experiment logs, or partially processed data sets. This access might come from a collaboration partner, a shared cloud bucket, a support request, an internal researcher, or an overlay permissive API. At this stage, nothing looks suspicious. Now, step 2. Feature extraction. Using machine learning tools, the attacker analyzes correlations across experiments, models noise distributions, tracks drift over time, identifies response patterns to control changes. Importantly, this does not require proprietary algorithms. Open source ML tools are sufficient. The barrier to entry is expertise, not access to secret code. Now, step 3, inference of latent properties. Over time, the attacker infers device-specific noise fingerprints, qubit-to-qubit variation patterns, environmental coupling signatures, sensitivity to particular controls. These properties were never written down, were learned implicitly by your own optimization systems, represent real competitive advantage. At this point, the attacker knows things about your system that are not in your documentation. Step 4, exploitation. What happens next depends on the actor's motivation. They might accelerate their own R&D, clone performance characteristics, design targeted interference strategies, or undermine differentiation in the market. Crucially, you may never know this happened. There is no obvious breach, no alarm goes off, no system crashes. Quantum devices are highly individual, sensitive to environment, and difficult to reproduce. That makes learned operational knowledge extremely valuable. If someone can reconstruct how your device behaves, what its weaknesses are, and how it responds to tuning, they can leverage that publications alone cannot provide. This is why telemetry is a crown jewel. Most organizations, they rely on authentication, authorization, encryption at rest and in transit. Those controls answer who can access the data. They don't answer what can be inferred from the data. Reverse engineering risk is about inference, not access alone. If someone is legitimately allowed to see the data, traditional security controls are silent. From a legal standpoint, this scenario threatens trade secret protection. If sensitive operational knowledge is embedded in data and that data is widely shared and protections are minimal, then a court may conclude you did not take reasonable steps to protect this information. That can destroy trade secret claims even if no breach occurred. If inferred device behavior enables replication of controlled technology or understanding of restricted performance characteristics, then sharing telemetry may constitute a de facto export of controlled technical information. This is particularly risky in international collaborations. Intent doesn't matter here, effect does. One of the most uncomfortable truths about this scenario is it is almost impossible to detect after the fact. You cannot easily tell who trained what model, what inferences they made, or what conclusions they drew. This makes prevention and limitation far more important than detection. At this stage, we are not listing controls. That comes later. But conceptually, mitigation requires treating telemetry as sensitive IP, minimizing sharing by default, assuming ML-based inference is possible, and governing downstream use, not just access. This requires a cultural shift, not just technical tools. We start with this scenario because it does not rely on exotic attackers. It does not require sophisticated exploits, and it is already feasible today. If you handle quantum telemetry casually, this risk is already present. Now that we have seen how data alone can be weaponized through AI, the next scenario raises the stakes further. The next presentation examines what happens when AI doesn't just observe systems but actively controls them. That's where silent failures become operational disasters. If you work on AI, security, or law and want to understand what actually gets you sued and what should change, you're in the right place. So subscribe to my channel, The AI Law, and I'll see you in the next episode of the series. This channel analyzes AI security legal risk, AI liability in practice, and AI governance compliance risk. We look at how AI system design, architecture, and runtime controls, they create legal risk in AI systems, AI model vulnerabilities and compliance failures, AI runtime controls and legal exposure, and how AI tooling risk translates to law for developers, security engineers, and governance teams. Threat Scenario 2: Manipulation of ML-controlled calibration and control loops. In the previous presentation, we saw a threat scenario where AI is used to observe and infer properties of a quantum system. In this scenario, the stakes are higher. Here, AI does not merely analyze the system, mind you. It acts on the system. This is the moment when AI for quantum systems become true cyber-physical systems, and when security failures, they stop being abstract and start becoming operationally dangerous. It's important to say this clearly here. If you are a quantum vendor or developer, you will use AI in control and calibration. Manual calibration does not scale. Expert-only tuning does not scale. Human-in-the-loop only systems do not scale. The research paper makes this explicit by highlighting AI-driven optimization of control voltages, pulse parameters, calibration routines, and feedback loops. Once AI is in the control loop, the threat model must change. I'm Nupur Mitra, a legal and governance risk translator for AI systems. On the AI Law, my channel, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, rights issues, and the future of jurisprudence. At a high level, this scenario involves an AI system that generates or updates control parameters. That system relies on data, rewards, or feedback signals. A threat actor manipulates some part of that pipeline. The AI system deploys harmful or suboptimal control decisions. The system degrades silently or catastrophically. Crucially, the AI may still be working as designed. This class of failure is well documented in other domains: industrial control systems, algorithmic trading, autonomous robotics. The difference here is that quantum systems are fragile, performance margins are narrow, and detection is harder. This makes control loop manipulation particularly dangerous. Attack vector 1. Data poisoning. Let's start with the simplest attack vector. Data poisoning. It occurs when training or feedback data is altered, biased, or selectively filtered. In a quantum calibration context, this might involve skewed measurement results, injected noise patterns, missing failure cases. The AI optimizes against the data it sees. If the data lies, the AI learns the wrong lesson. Attack vector 2. Reward manipulation. Many control systems rely on objective functions, reward signals, performance metrics. If a threat actor can influence which metrics are reported, change thresholds, or subtly redefine success, the AI may optimize toward outcomes that look good numerically but are operationally harmful, and this is known as reward hacking. Attack vector 3. Model substitution. In some cases, the attacker doesn't need to touch the data. If they can swap a trained model, alter its configuration, or downgrade its version, they can influence behavior directly. This is especially dangerous when model updates are frequent, deployments are automated, and review is minimal. Attack vector 4. Feedback loop instability. Even without malicious intent, complex control loops, they can oscillate, overcorrect, or diverge. A knowledgeable advisory can exploit this by nudging parameters just enough, timing interventions carefully, making failures look like normal instability. This creates plausible deniability. One of the most dangerous aspects of this scenario is that failure may be subtle. Instead of a system crash or a clear malfunction, you may see gradually declining fidelity, increased error rates, inconsistent experimental results, unexplained downtime. These systems are often attributed to hardware aging, environmental noise, or quantum weirdness that makes malicious manipulation extremely hard to identify. The impact of this scenario can include wasted experimental time, damaged hardware, loss of customer trust, breach of service level agreements, reputational harm. In some cases, the systems may still produce results, but they are wrong. From a customer perspective, that is often worse than a clear failure. From a legal standpoint, this scenario raises several issues. Duty of care. Was it reasonable to deploy AI without guardrails? Foreseeability. The risks of machine learning control are well known in other domains. Liability. Who is responsible when an AI control system causes harm? If these systems are customer-facing, the stakes increase further. Traditional security focuses on perimeter defense, authentication, patching. None of those directly address poisoned training data, reward manipulation, model drift, or even silent degradation. This requires ML-specific governance, not just IT controls. The most important takeaway from this scenario is when AI controls hardware, correctness becomes a security property. Security is no longer just about keeping attackers out. It's about ensuring the system behaves safely and as intended over time. We are not yet prescribing solutions in detail, but conceptually, mitigation requires strict control over model deployment, visibility into control outputs, anomaly detection beyond simple thresholds, and the ability to roll back safely. Most importantly, it requires acknowledging that AI can fail silently. So far, we have seen AI used to infer secrets from data. AI used to control systems in potentially dangerous ways. In the next episode of the series, we look at a different angle. What happens when AI generates executable artifacts like quantum circuits that flow through your platform and supply chain? That's the focus of the next episode to come. If you work on AI, security, or law and want to understand what actually gets you sued and what should change, you're in the right place. So subscribe to my channel, The AI Law, and I'll see you in the next episode of the series. This channel analyzes AI security legal risk, AI liability in practice, and AI governance compliance risk. We look at how AI system design, architecture, and runtime controls, they create legal risk in AI systems, AI model vulnerabilities and compliance failures, AI runtime controls and legal exposure, and how AI tooling risk translates to law for developers, security engineers, and governance teams. Up to now, we have looked at threats where AI, it learns from data or controls system behavior. In this scenario, AI does something subtly different, but equally dangerous. It produces executable artifacts. In other words, AI doesn't just influence decisions. It creates instructions that your system will execute. That distinction matters enormously from a security and legal perspective. Generative AI is increasingly used to propose quantum circuits, optimize gate sequences, reduce depth or noise sensitivity, warm start compilers. This makes sense. Quantum circuit design is combined complex, hardware dependent, and extremely time consuming for humans. Generative models, they promise speed, creativity, and exploration of large design spaces. This research paper highlights this direction explicitly. I'm Nupur Mitra, a legal and governance risk translator for AI systems. On the AI Law, my channel, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, rights issues, and the future of jurisprudence. Anytime software generates something executable, you have a supply chain. In classical software, we already understand this. Code generation tools, package managers, CI/CD pipelines. Quantum systems now face the same issue. AI-generated circuits, they become inputs to execution pipelines. That means they must be trusted, validated, and attributable. So if they are not, you are a supply chain vulnerability. Let's walk through how this threat scenario unfolds. Step 1. Model access. The attacker gains access to a generative model, its prompt interface, or a system that consumes its outputs. This may be an internal tool, a customer-facing feature, or a shared research environment. No breach is required, just access. Step 2. Malicious or pathological generation. The attacker crafts inputs that cause the model to generate circuits with pathological properties, exploit edge cases in the compiler, stress hardware in unexpected ways, or encode hidden patterns. These circuits may appear valid, pass superficial checks, and look creative or novel. Step 3. Downstream execution. Because the circuits are syntactically correct, produced by a trusted tool, they flow through compilers, schedulers, control systems, and are eventually executed on real hardware. At this point, damage can occur. The harm from this scenario is varied and often subtle. It can include denial of service via resource exhaustion, accelerated hardware degradation, silent corruption of results, leakage of information through side channels, or customer IP contamination. Notably, the AI may not be wrong. It may simply be optimizing for something misaligned with safety or trust. This scenario is hard to defend because generated circuits can be novel, exhaustive validation is expensive, and correctness is context dependent. Traditional security approaches struggle here because there is no signature to match, no known exploit, and no obvious malware. Everything looks like legitimate work. One of the most serious challenges here is provenance. When a circuit is generated, who's responsible for it? Which model version produced it? What data influenced that model? Can the result be reproduced? Without provenance, you cannot investigate incidents, assign responsibility, or defend yourself legally. From a compliance standpoint, this is unacceptable. Generative models trained on proprietary circuit libraries, customer workloads, or restricted datasets can unintentionally reproduce patterns, leak design strategies, or embed protected IP. This creates licensing disputes, customer claims, and regulatory scrutiny. Even unintentional leakage can be actionable. If a vendor deploys generative systems that directly produce executable instructions without appropriate safeguards, they may be seen as negligent or failing to meet industry standards. This is especially true if harm is forcible and controls were available but not implemented. Quantum systems amplify this risk because hardware is scarce and expensive, experiments are costly, and correctness is difficult to verify independently. A bad circuit doesn't just waste compute. It can waste weeks of cryogenic runtime. A dangerous assumption here is if the model is internal, we trust it. Trusting a model is not a security control. Models can behave unpredictably in code bias or be manipulated indirectly. The supply chain mindset applies regardless of where the model lives. Again, we're not listing controls yet, but mitigation conceptually requires strong validation of generated artifacts, clear provenance and audit trails, constraints on what models are allowed to produce, and isolation between generation and execution. Without these, generative AI becomes a blind spot. This threat is not theoretical. Any organization using AI-assisted circuit generation, auto-optimization, or exploratory design tools is already exposed to this risk. Ignoring it doesn't make it go away. So far, we've seen threats that extract knowledge, manipulate control, and compromise the supply chain. The next scenario looks deeper into the stack. What happens when the components that ensure correctness, like error correction decoders and accelerators, are themselves compromised? That's the focus of the next video. If you work on AI, security, or law and want to understand what actually gets you sued and what should change, you're in the right place. So subscribe to my channel, The AI Law, and I'll see you in the next episode of the series. This channel analyzes AI security legal risk, AI liability in practice, and AI governance compliance risk. We look at how AI system design, architecture, and runtime controls, they create legal risk in AI systems, AI model vulnerabilities and compliance failures, AI runtime controls and legal exposure, and how AI tooling risk translates to law for developers, security engineers, and governance teams. In the previous scenario, we examined how generated artifacts, quantum circuits, they can introduce supply chain risk. In this scenario, we go one layer deeper. We are now attacking the part of the system that everyone implicitly trusts, the mechanisms that are supposed to ensure correctness. In quantum systems, that mechanism is error correction, and increasingly AI-based decoders running on accelerators. If this layer is compromised,
The system may continue operating while silently producing incorrect results. That is one of the most dangerous failure modes imaginable. Quantum error correction is mathematically complex, performance critical, difficult to verify externally, and deeply intertwined with hardware behavior. AI is attractive here because decoders must be fast, adaptive, and hardware specific. This research paper explicitly discusses AI-based decoders, accelerator implementations, and the performance benefits of GPUs and FPGAs. From a security perspective, this combination is extremely sensitive. I'm Nupur Mitra, a legal and governance risk translator for AI systems. On the AI Law, my channel, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, rights issues, and the future of jurisprudence. At a high level, the scenario looks like this. A decoder model or accelerator implementation is altered. The alteration is subtle enough to avoid detection. Decoding behavior is biased, degraded, or manipulated. Logical errors increase or results become skewed. Users trust outputs that are no longer reliable. This is a silent integrity failure. From an attacker's perspective, decoders are ideal targets because they sit deep in the stack. They are rarely audited and failures are hard to distinguish from normal noise. Front-end breaches get attention, decoder failures get blamed on physics. This asymmetry makes them attractive. Attack vector 1, model weight manipulation. If decoders are ML-based, then model weights are executable logic. An attacker who can alter weights, swap model versions, or influence training data can change decoding behavior without changing any code. This is particularly dangerous if models are deployed automatically, signatures are not enforced, or versioning is weak. Attack vector 2, firmware and bitstream tampering. When decoders run on FPGAs, custom ASICs, or specialized accelerators, the bit streams and firmware, they become critical. Tampering here can introduce backdoors, bias certain error patterns, or degrade performance conditionally. These modifications are opaque, persistent, and difficult to reverse engineer. Attack vector 3, runtime and dependency compromise. Decoders often rely on ML frameworks, numerical libraries, hardware drivers. A compromised dependency can subtly alter behavior, leak information, or create targeted faults. Because these components are plumbing, they receive less scrutiny. The most dangerous aspect of this scenario is that nothing obviously breaks. Instead, you may observe slightly worse logical error rates, unexplained performance variability, inconsistencies between runs, and customer complaints about reproducibility. These are often dismissed as device instability, environmental noise, or expected variance. This delays detection. The business impact can be severe. Customers lose confidence in results. Benchmarks and claims, they become unreliable. Service level agreements are violated and reputational damage accumulates. In regulated or high-stake environments, this can end customer relationships permanently. From a legal perspective, this scenario raises questions about reasonable security controls, software supply chain management, and duty to ensure correctness. If a vendor cannot demonstrate integrity protections, provenance, and monitoring, they may be found negligent even in the absence of proof of malicious intent. A key conceptual shift here is this. In AI-driven quantum systems, correctness is a security property, not just a scientific one. If users cannot trust results, the system has failed in a security-relevant way. This is different from classical IT, but analogous to financial systems producing incorrect balances, medical devices producing incorrect readings. Detecting this kind of compromise is difficult because there is no known good baseline at scale. Hardware variability masks anomalies, and testing is expensive. This means that preventive controls matter more than reactive detection. At a high level, mitigating this risk requires treating decoders and bit streams as critical infrastructure, enforcing strong integrity guarantees, limiting who can modify or deploy them, and maintaining evidence of correctness over time. We'll return to these ideas when we discuss controls and compliance in the episodes to come. Even with trusted engineers, good intentions, and strong culture, mistakes can happen. A misconfigured update pipeline or unreviewed dependency, they can have the same effect as an attack. Security must account for both. So far, we've examined threats that target data, control loops, generated artifacts, and correctness mechanisms. The next scenario broadens the lens to something less technical but equally dangerous: legal and regulatory failure due to export controls and cross-border access. That's where we go next.
If you work on AI, security, or law and want to understand what actually gets you sued and what should change, you're in the right place. So subscribe to my channel, The AI Law, and I'll see you in the next episode of the series. This channel analyzes AI security legal risk, AI liability in practice, and AI governance compliance risk. We look at how AI system design, architecture, and runtime controls, they create legal risk in AI systems, AI model vulnerabilities and compliance failures, AI runtime controls and legal exposure, and how AI tooling risk translates to law for developers, security engineers, and governance teams.
Up to this point, we've been talking about threats that look technical: data inference, control loop manipulation, supply chain compromise, decoder integrity failures. Now, this video is about a different kind of threat, one that often causes more damage than any cyber attack: legal and regulatory failure. In quantum technology, some of the most severe security incidents are not breaches at all. They are violations of export control and deemed export laws discovered after the fact. Quantum technology already sits in a sensitive regulatory category in many jurisdictions. When you combine quantum systems with AI, you introduce automation, abstraction, and data-driven inference, which makes it much harder to intuitively understand what counts as controlled technical information. This research paper does not mention export controls, but it describes exactly the kinds of capabilities that regulators care about: improved device performance, accelerated scaling, and advanced control and error correction techniques.
I'm Nupur Mitra, a legal and governance risk translator for AI systems. On the AI Law, my channel, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, rights issues, and the future of jurisprudence.
This threat scenario does not begin with an attacker. It begins with a perfectly normal business or research activity. For example, a foreign national engineer joins your team. A collaborator overseas, he accesses a dataset. A cloud training job runs in another region. A partner receives detailed performance telemetry. No one intends to violate the law, but intent is irrelevant. Let's walk through how this scenario typically unfolds. Step 1. Sensitive information exists. Your organization possesses telemetry revealing device behavior, trained models encoding calibration strategies, performance benchmarks, or advanced decoder implementations. Some of this information may be export controlled, even if it doesn't look like a blueprint. Step 2. Information crosses a legal boundary. That information becomes accessible to a foreign national employee, an overseas collaborator, a cloud system in another jurisdiction. This can happen through shared cloud storage, internal tools, model access, or collaborative notebooks. At this point, a deemed export may have occurred. Step 3. Discovery, often much later. Export violations are rarely discovered immediately. They're often uncovered during audits, due diligence for acquisitions, government inquiries, or unrelated investigations. By the time they're discovered, the exposure may have been ongoing for months or years. Traditional export control focused on physical items, schematics, and explicit technical documents. But AI for quantum systems break those assumptions. Sensitive knowledge may now live in trained model weights, learned representations, configuration files, or derived metrics. This raises difficult questions. Is a trained model controlled? Is telemetry controlled? Is inference itself a controlled activity? Regulators increasingly answer yes to some of these. A key concept here is deemed export. A deemed export occurs when controlled technical information is released to a foreign national, even within the same country. This means access control matters as much as geography. HR, IAM, and engineering systems, they intersect legally. Many organizations fail here because engineers are not trained on deemed export rules. Access is granted broadly for collaboration. Systems are not nationality aware. Cloud usage introduces additional complexity. Questions regulators may ask include: where is the data stored? Where is it processed? Who can access it? Which regions host training jobs? Running ML training in another region can constitute an export, even if no human touches the data. This surprises many teams. The consequences of export control violations can include substantial fines, criminal liability in extreme cases, loss of export privileges, contract termination, reputational damage. For startups and vendors, loss of export privileges can be existential. At this point, it's worth emphasizing export compliance failure is a security issue, not just a legal one. Why? It can halt operations. It can trigger government oversight. It can force architectural changes under pressure. It can undermine customer trust. Security teams must be involved because controls must be technical, not just policy-based. Organizations often fail here because exploit classification is treated as a one-time exercise. Controls rely on training rather than enforcement. Research environments are exempted for speed. Cloud defaults are not reviewed through a compliance lens. These are predictable failures and therefore preventable. At a high level, mitigating this risk requires clear export classification of data, models, and software. Access controls tied to nationality and role. Region-aware cloud architectures. Collaboration review processes. This is not about slowing innovation. It is about preventing catastrophic legal exposure. This slide belongs in the threat scenario section because its impact rivals or exceeds technical breaches. Its likelihood is high in collaborative environments, and its detection is often delayed. Ignoring it is not an option for quantum vendors. At this point, we have walked through 5 concrete threat scenarios: machine learning-based reverse engineering, control loop manipulation, generative circuit supply chain risk, decoder and accelerator compromise, export control and deemed export failure. The natural next question is, how do we defend against all of this without stopping innovation? So the next episodes to come would shift from threat modeling to controls and compliance, starting with security engineering fundamentals tailored to AI for quantum systems. If you work on AI, security, or law and want to understand what actually gets you sued and what should change, you are in the right place. Subscribe to my channel. This channel analyzes AI security legal risk, AI liability in practice, and AI governance compliance risk. We look at how AI system design, architecture, and runtime controls, they create legal risk in AI systems, AI model vulnerabilities and compliance failures, AI runtime controls and
and legal exposure, and how AI tooling risk translates to law for developers, security engineers, and governance teams.
Up to now, this series has been intentionally uncomfortable. We have identified sensitive assets, named realistic threat actors, mapped attack surfaces, and walked through concrete failure scenarios. At this point, a natural reaction is, are we supposed to stop using AI? Are we supposed to slow down development? Are these risks even manageable? This episode exists to reset the tone. The answer to all of those questions is no. The goal is not fear. The goal is control with confidence. Many organizations instinctively reach for familiar frameworks: network segmentation, identity and access management, patching and vulnerability scanning. Those are necessary, but they're not sufficient. Why? Because AI for quantum systems are data-driven, model-mediated, and cyber-physical. Traditional security frameworks assume deterministic software, human-authored logic, and static behavior. None of those assumptions hold here. This slide introduces the control philosophy that must replace them. I'm Nupur Mitra, a legal and governance risk translator for AI systems. On the AI Law, my channel, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, rights issues, and the future of jurisprudence. If you work on AI, security, or law and want to understand what actually gets you sued and what should change, you are in the right place. Core Principle 1. In many organizations, code is protected, data is just data, models are treated as byproducts. That hierarchy is wrong for AI for quantum systems. Here, data and models often matter more than code. Telemetry, learned representations, and control outputs must be classified, access controlled, logged, and governed. If it influences system behavior or encodes knowledge, it is a security asset. Core Principle 2. A critical mindset shift is this: if you can learn something from data using AI, assume someone else can too. This means don't rely on its too noisy as protection, don't assume aggregation removes sensitivity, don't treat derived metrics as harmless by default. Controls must be designed with inference risk in mind, not just access risk. Core Principle 3. Many security programs focus on detecting intrusions, stopping obvious misuse, responding to outages. AI for quantum threats are different. The most damaging failures are silent, gradual, and plausibly deniable. This requires baseline monitoring, drift detection, and correctness validation over time. You must assume things can go wrong quietly. Core Principle 4. Policies alone are insufficient. Saying don't share sensitive data or follow export rules does nothing if systems allow violations by default. Governance must be enforced through IAM, embedded in pipelines, and visible in logs. If a control cannot be enforced technically, it will eventually be bypassed unintentionally. Core Principle 5. Controls must exist across the entire life cycle: data collection, model training, deployment, execution, and retirement. Securing only one stage creates blind spots. For example, secure training means little if deployment is unverified. Secure deployment means little if data is overshared. Secure hardware means little if models are untrusted. Lifecycle thinking is essential. So, at this point, it's important to emphasize well-designed controls enable innovation. They reduce uncertainty, they accelerate customer trust, and they simplify audits, and also they prevent costly rework. Organizations with clear control frameworks move faster in regulated environments, close enterprise deals more easily, and avoid disruptive surprises. This is not about saying no, it's about being able to say yes safely. So starting with the next episode, we'll move from philosophy to action. Controls will be organized into clear domains: data governance, ML governance, secure supply chain, hardware and accelerator integrity, platform and cloud security, export compliance, customer assurance, and auditability. Each domain maps directly to the threat scenarios we have discussed earlier in the earlier episodes. I know a common objection here may be, we're too early for this level of control. The reality is, early stage systems are easier to secure, early decisions are cheaper to fix, and early discipline prevents technical debt. Waiting until scale guarantees pain. Controls can be lightweighted, incremental, and proportional, but they must exist. Another important point for vendors. In quantum markets, trust is a product feature. Customers cannot easily verify correctness, integrity, or long-term reliability. They rely on your controls, your transparency, and your governance. Security maturity will increasingly differentiate vendors. So now, the next several episodes will be more concrete and operational. We will break controls into checklists, explain why each exists, and show how they mitigate specific threats. This is where theory turns into engineering practice. Now, with the control philosophy established, the logical place to start is data, because data is where most of these risks originate. So the next video dives into data governance controls for AI for quantum systems. If you work on AI, security, or law and want to understand what actually gets you sued and what should change, you are in the right place. Subscribe to my channel. This channel analyzes AI security legal risk, AI liability in practice, and AI governance compliance risk. We look at how AI system design, architecture, and runtime controls, they create legal risk in AI systems, AI model vulnerabilities and compliance failures, AI runtime controls and legal exposure, and how AI tooling risk translates to law for developers, security engineers, and governance teams. Let's understand today as to why data governance comes first. If you remember only one thing from this entire series up till now, it should be this. In AI for quantum systems, data is the root of almost every major risk. Every threat scenario we've discussed so far, reverse engineering, control loop manipulation, generative supply chain risk, decoder compromise, expert control failure. Either they start with data or is amplified by data. That's why data governance is not an afterthought here. It is the foundation. So let's talk specifically about quantum telemetry. Telemetry in classical systems is often noisy, generic, and largely interchangeable across systems. Quantum telemetry is different. Quantum telemetry encodes device-specific behavior, captures environmental interactions, reflects tuning and calibration decisions, and changes over time in meaningful ways. From an AI perspective, this is gold. From a security perspective, it is a high-value, high-risk asset. I'm Nupur Mitra, a legal and governance risk translator for AI systems. On the AI Law, my channel, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, rights issues, and the future of jurisprudence. Most organizations make one of these two mistakes. Either they treat telemetry as just logs, or they assume aggregation or anonymization removes sensitivity. Both of these assumptions are wrong. AI thrives on noisy data, aggregated signals, and subtle correlations. What looks harmless to a human analyst may be extremely revealing to a model. The goal of data governance here is not to stop people from using data. The goal is to control who can access which data, for what purpose, for how much long, in which direction, in which jurisdiction, and with what downstream rights. This is about intentional data use, not restriction for its own sake. Control 1. The first concrete control is classification. Generic labels like internal or confidential are insufficient. Quantum vendors should introduce classifications such as restricted device telemetry, restricted derived device models, restricted customer circuits, controlled export-sensitive technical data. Classification must reflect inference risk, export sensitivity, and competitive value. If data isn't labeled correctly, it cannot be protected correctly. Control 2. Traditional access control answers, is this person allowed to see this data? That is not enough. AI for quantum systems require purpose-based access. Is this data being accessed for an approved purpose? Let's take some examples. Debugging a specific incident, training a specific model, performing a specific analysis. Controls should enforce scoped access, time-bound access, and explicit justification. This dramatically reduces accidental misuse and oversharing. Control 3. One of the most important practical controls is data separation. Raw telemetry should be tightly restricted, accessed by fewer people, and stored separately from derived data sets. Derived data sets should be purpose-specific, minimized, and stripped of unnecessary detail. This limits blast radius if data is misused or leaked. Control 4. You cannot protect what you cannot see. Every access to sensitive quantum data should be logged, attributable, and reviewable. This includes downloads, API access, model training jobs, and even data exports. Audit logs serve multiple purposes: security monitoring, forensic analysis, export compliance evidence, and customer assurance. Lack of logs is often interpreted legally as lack of control. Control 5. Export compliance cannot be bolted on later. Data governance must integrate export classification, nationality-aware access controls, region-aware storage and processing. For example, certain datasets may be accessible only to specific nationals. Training jobs may be restricted to certain cloud regions. Exports may require approval workflows. This must be enforced technically, not manually. Control 6. Collaboration is essential in quantum development, but dangerous without controls. Controls should include explicit approval for external sharing, clear usage limitations in agreements, expiration and deletion requirements, and audit rights where feasible. The default posture should be no external sharing without explicit intent. This protects both IP and compliance posture. Control 7. Finally, vendors must track where data goes. This includes which models were trained on which datasets were shared externally, which outputs were derived from which inputs. Without lineage, you cannot assess contamination, you cannot respond to incidents, and you cannot answer regulator questions. Lineage is not optional once AI is involved. A common concern is this will slow down research. In practice, the opposite is often true. Clear data governance reduces ambiguity, prevents last-minute legal blocks, and enables faster approvals. Researchers waste less time wondering what they are allowed to do. Let's connect this back to the threats we discussed. Reverse engineering, limited telemetry access, control loop poisoning, controlled training data, export violations, region and nationality-aware controls, IP leakage, purpose-bound sharing. Data governance is the first and most effective line of defense. Data governance alone is not enough. Once data feeds models, models themselves become critical assets. The next video focuses on ML governance, how models are trained, versioned, deployed, and monitored. This is where many organizations fail today. If you work on AI, security, or law and want to understand what actually gets you sued and what should change, you are in the right place. Subscribe to my channel.
This channel analyzes AI security legal risk, AI liability in practice, and AI governance compliance risk. We look at how AI system design, architecture, and runtime controls, they create legal risk in AI systems, AI model vulnerabilities and compliance failures, AI runtime controls and legal exposure, and how AI tooling risk translates to law for developers, security engineers, and governance teams.
Control domain 2. After data, the next most critical control domain is machine learning governance. This deserves special attention because ML is not just another software component or a performance optimization. In AI for quantum systems, ML models encode system knowledge, make operational decisions, and influence physical behavior. That means models are infrastructure. If you treat them like disposable artifacts, you create systemic risk. Most engineering organizations are good at governing source code, binaries, configuration files. ML artifacts don't fit neatly into that model. So the key differences are behavior is learned, not authored. Training data matters as much as code. Outputs are probabilistic and changes can be subtle but impactful. So governance must adapt accordingly. I'm Nupur Mitra, a legal and governance risk translator for AI systems. On the AI Law, my channel, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, rights issues, and the future of jurisprudence. The goal of ML governance is to ensure that every model is attributable, every deployment is intentional, every change is detectable, and every failure is traceable. This is about control and accountability, not stifling experimentation. The first requirement is deceptively simple. Know which models exist. This includes training time models, production models, experimental variants, and deprecated versions. Each model should have a unique identifier, an owner, and a documented purpose. Orphaned models are security risks. Control 2. Models must be versioned, immutable once approved, and reproducible. Why this matters? Silent weight changes are hard to detect. Rollback attacks are possible, and forensic analysis requires exact replicas. A model registry with immutability guarantees is essential. Control 3. Models are executable logic. They should be treated like binaries. This means signing trained models, verifying signatures at load time, rejecting unsigned or tampered artifacts. This is especially important when models control hardware or run on accelerators. Without signing, model substitution attacks are trivial. Control 4. For every model, you should be able to answer which data was used, which code version trained it, which hyperparameters were chosen, and who initiated training. This lineage is critical for debugging, compliance, and incident response. And if you can't reproduce a model, you can't trust it. Control 5. Not every trained model should be deployable automatically, especially for those models that influence control loops, affect correctness, or serve customers. Deployment should include explicit approval, automated checks, and environment-specific constraints. This prevents accidental or malicious deployment. Control 6. Once deployed, models must be monitored. This includes output distributions, performance metrics, stability indicators, and anomaly signals. In AI for quantum system, drift can indicate hardware changes, data poisoning, or model degradation. Monitoring is your early warning system. Control 7. No model should be a single point of failure. Systems must support reverting to a known good model, switching to conservative control modes, or pausing automation when anomalies occur. This is essential for safety, availability, and customer trust. Control 8. Research experimentation is vital, but dangerous when mixed with production. Controls should enforce separation of environments, different deployment paths, different access privileges. Experimental models should never reach production accidentally. Control 9. Not everyone who can train a model should be able to deploy it. Access controls should distinguish between training, evaluation, deployment, and modification. Least privilege applies here as much as anywhere else. So let's tie this back to the threats: model substitution, signing, and immutability; poisoned training, lineage, and reproducibility; silent degradation, monitoring, and rollback; decoder compromise, deployment gates. ML governance directly addresses the highest risk scenarios we discussed. Many teams say these are research models, but once a model influences control, affects correctness, or touches customer workloads, it is operational. The line between research and production is not a legal defense. Strong ML governance reassures customers, simplifies audits, accelerates enterprise sales, and prevents existential incidents. It turns AI from a liability into an asset. So far we have governed data and models. Next, we must govern how software and artifacts they move through the organization. So the next episode focuses on secure supply chain controls, because AI for quantum stacks are only as strong as their weakest dependency. If you work on AI, security, or law and want to understand what actually gets you sued and what should change, you are in the right place. Subscribe to my channel. This channel analyzes AI security legal risk, AI liability in practice, and AI governance compliance risk. We look at how AI system design, architecture, and runtime controls, they create legal risk in AI systems, AI model vulnerabilities and compliance failures, AI runtime controls and legal exposure, and how AI tooling risk translates to law for developers, security engineers, and governance teams. At this point, we've governed data and models. But there is a dangerous illusion that can creep in here. If our data and models are controlled, we are safe. That's not true. In AI for quantum systems, almost nothing runs in isolation. Everything depends on libraries, frameworks, drivers, firmware, build systems, and deployment pipelines. This video is about the supply chain, the part of the system most likely to be compromised without anyone noticing it. Quantum systems bring together three high-risk domains: advanced hardware, machine learning frameworks, highly specialized control software. Each of these has deep dependency trees, fast-moving ecosystems, and opaque components. When combined, they create a fragile trust chain. An attacker doesn't need to target your core IP. They only need to compromise something you trust. I'm Nupur Mitra, a legal and governance risk translator for AI systems. And on my channel, The AI Law, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, rights issues, and the future of jurisprudence. The goal of supply chain security is simple in concept. You must know what you are running, where it came from, and whether it has been altered. In practice, achieving this requires discipline and tooling. Control 1. The foundation of supply chain security is visibility. You must maintain an SBOM, Comprehensive Software Bill of Materials, that covers control software, ML training pipelines, inference runtimes, decoders, firmware, and build tooling. This includes open source libraries, proprietary components, and third-party binaries. Without an SBOM, you cannot assess risk or respond to vulnerabilities. Control 2. Floating dependencies are a liability. Quantum vendors should pin library versions, control upgrade windows, and test changes deliberately. This reduces the risk of sudden behavioral changes, malicious package updates, or incompatibilities affecting correctness. Speed without control leads to fragility. Control 3. Build systems are high-value targets. Controls should include isolated build environments, reproducible builds, limited access to signing keys, and logging of build actions. If an attacker can compromise the build, everything downstream is suspect. Control 4. Every artifact that moves through the pipeline should be signed at creation, verified at use. This includes binaries, containers, machine learning models, firmware images. Verification should happen automatically at deployment or load time. Unsigned artifacts should not run. Control 5. Not all dependencies are equal. Quantum vendors should identify critical dependencies. They should assess their security posture. They should monitor their update practices. So, for high-impact components, this may include code review, vendor security attestations, or contractual requirements. Blind trust is not a strategy. Control 6. Control 6. Once you know what you are running, you must monitor vulnerability disclosures. You must assess relevance quickly and patch deliberately. This includes open source CVEs, firmware advisories, and hardware errata. Response plans should be documented and rehearsed. Control 7. Mixing environments is a common failure mode. Controls should enforce separation between development and production pipelines, distinct credentials and keys, and promotion gates. This limits blast radius if something goes wrong. Control 8. Machine learning frameworks and accelerator runtimes, they deserve special attention because they run privileged code, they change frequently, and they are hard to inspect. Controls may include frozen framework versions, controlled upgrade cycles, sandboxing where possible. Performance gains should never come at the cost of integrity. Supply chain controls, they directly mitigate decoder compromise, generative circuit injection, control plane manipulation via dependencies, and silent behavioral changes. They also improve your ability to detect anomalies, prove diligence, and respond to incidents. Increasingly, customers and regulators, they expect SBOMs, supply chain controls, and vulnerability management processes. This is no longer optional, especially for advanced technology vendors. Failing here is seen as negligence. Small teams often say, "We don't have the resources for this." In reality, smaller stacks are easier to inventory. Fewer dependencies means simpler SBOMs. Early discipline prevents future chaos. The cost of doing nothing is far higher. So now we've covered data, models, and software artifacts. The next video moves deeper into the stack: hardware, firmware, and accelerator integrity. This is where quantum systems differ most sharply from traditional IT. If you work on AI, security, or law and want to understand what actually gets you sued and what should change, you are in the right place. Subscribe to my channel.
This channel analyzes AI security legal risk, AI liability in practice, and AI governance compliance risk. We look at how AI system design, architecture, and runtime controls, they create legal risk in AI systems, AI model vulnerabilities and compliance failures, AI runtime controls and legal exposure, and how AI tooling risk translates to law for developers, security engineers, and governance teams.
Up to this point, much of what we have discussed could apply, at least in spirit, to other AI systems. This video marks a turning point. Quantum systems are fundamentally cyber-physical. At this layer, traditional software security assumptions begin to fail. You cannot simply patch physics. Behavior is not deterministic, and subtle changes can have disproportionate effects. This is why hardware, firmware, and accelerator integrity, they deserve their own control domain. Quantum vendors rely on specialized control electronics, firmware-driven timing and pulses, GPUs and FPGAs for real-time decoding and control, hardware accelerators tightly coupled to software logic. If these components are compromised, everything above them becomes untrustworthy and detection is extremely difficult. So this is the deepest trust layer in the system. I'm Nupur Mitra, a legal and governance risk translator for AI systems, and on my channel, The AI Law, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, rights issues, and the future of jurisprudence. The core risk is not just downtime. The core risk is silent correctness failure. If hardware or firmware, they behave incorrectly, results may look plausible, errors may be attributed to noise, and customers, they may never know that the outputs were compromised. So that is existential for a quantum vendor. The goal of hardware and accelerator integrity controls is to ensure that only approved firmware and bit streams run. Changes are intentional and traceable, and behavior can be attested to a known state. This is about trust at the bottom of the stack. Control 1. Secure boot ensures that firmware and bit streams are verified at startup. Unauthorized code cannot execute. For quantum systems, this may apply to control electronics, FPGA-based decoders, embedded controllers. Even partial secure boot coverage is better than none. Control 2. Firmware and bit streams, they should be cryptographically signed, verified before execution, because this prevents accidental deployment of incorrect images, malicious tampering, rollback to vulnerable versions. Unsigned firmware should never run in production systems. Control 3. Firmware updates must be deliberate, reviewed, and logged. Ad hoc updates are dangerous. Controls should include approval workflows, version tracking, rollback plans. This is especially important when firmware interacts with machine learning driven control loops. 4. Where possible, systems should support attestation of firmware state. Verification that expected images are running. Even limited attestation, they increase confidence, they aid incident response, and they support customer assurance. Perfect attestation is not required. Progress matters. Control 5. For shared accelerators, isolate workloads, avoid cross-tenant leakage, and prevent residual state exposure. This is particularly important for GPU-based machine learning training, and shared FPGA pools. Isolated failures here can undermine both confidentiality and integrity. Control 6. Because detection is hard, monitoring matters. Indicators may include unexpected performance changes, unusual error patterns, and timing anomalies. These signals are noisy, but trends matter. Monitoring should focus on deviation from baseline, not absolute thresholds. Control 7. Hardware eventually ages, is pre-purposed, or decommissioned. Controls must ensure firmware is wiped or reset. Sensitive data is cleared and access is revoked. Old hardware is a frequent blind spot. Control 8. From a compliance perspective, it is not enough to do these things. You must be able to document firmware provenance, show update logs, demonstrate control ownership. Evidence matters as much as implementation. This layer is often neglected because it's complex, it involves multiple teams, and it's not purely security or engineering. But attackers and regulators don't care about organizational boundaries. If this layer fails, everything else fails. Hardware and accelerator integrity directly mitigates decoder compromise, silent correctness failures, supply chain attacks via firmware, control plane manipulation. It is the foundation that makes higher level controls meaningful. Many organizations, mind you, implicitly trust hardware because it comes from reputable vendors. It just works. Trust is not a control. Hardware must be governed like any other critical component. So in this series, we've now secured data, models, software supply chains, and hardware foundations. Now, the next episode of the series will address platform and cloud security, where customers and collaborators, they actually interact with your systems. That's where we go next. If you work on AI, security, or law and want to understand what actually gets you sued and what should change, you are in the right place. Subscribe to my channel. This channel analyzes AI security legal risk, AI liability in practice, and AI governance compliance risk. We look at how AI system design, architecture, and runtime controls, they create legal risk in AI systems, AI model vulnerabilities and compliance failures, AI runtime controls and legal exposure, and how AI tooling risk translates to law for developers, security engineers, and governance teams. Everything we've discussed so far, data governance, ML governance, supply chain security, hardware integrity, they can all still fail if the platform layer is weak. This is the layer where customers, they submit jobs, collaborators, they access systems, models, they are executed, and the results are delivered. In other words, this is where trust is exercised, not just designed. Quantum platforms, they combine scarce physical resources, shared execution environments, probabilistic outputs, and long execution times. Unlike classical cloud services, workloads are expensive, errors are ambiguous, and isolation failures, they may not be obvious. That makes platform security both critical and non-trivial. I'm Nupur Mitra, a legal and governance risk translator for AI systems. On my channel, The AI Law, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, risk issues, and the future of jurisprudence. The goal of platform and cloud security in AI for quantum systems is to ensure that users are isolated from each other. Access is least privilege and auditable. Execution cannot be abused or manipulated, and results, they are trustworthy. This is about protecting customers from each other and from you. Control 1. Every platform interaction should be authenticated, authorized, and attributable. This includes job submission, circuit upload, result retrieval, model invocation. IAM must support fine-grained rules, service identities, short-lived credentials. Shared credentials are unacceptable at this layer. Control 2. Multi-tenancy is unavoidable for most quantum platforms. Isolation must exist across data storage, execution queues, logs, and metadata, accelerator usage. Failures here can lead to data leakage, inference attacks, side channel exposure. Isolation must be enforced technically, not just contractually. Control 3. Quantum resources are scarce and expensive. Controls must prevent intentional resource exhaustion, accidental runaway jobs, adversarial circuit submissions. So this includes rate limiting, job size limits, scheduling fairness, and anomaly detection. Availability is a security property here. Control 4. Users may submit circuits, configuration files, optimization hints. These inputs must be validated to prevent malformed inputs, hardware stress patterns, pathological executions. Trusting user input blindly is dangerous, even from friendly customers. Control 5. Results often include raw measurement data, derived statistics, metadata about execution. Controls should ensure results are delivered only to authorized users. Metadata does not leak systems internals. Logs do not expose sensitive details. Metadata leakage is a common blind spot. Control 6. Platform actions must be logged centrally, correlated across layers, retained appropriately. Logs should support incident investigation, compliance audits, customer inquiries. So if you cannot reconstruct who did what, when, and why, you are exposed. Control 7. APIs and SDKs, they shape user behavior. Security considerations include input validation, clear error handling, rate limiting, versioning discipline. Poor API design often leads to accidental misuse that looks like attack traffic. Control 8. Platform security intersects directly with export compliance. Controls must ensure workloads run only in approved regions, data does not cross borders unintentionally, backups and replicas, they follow the same rules. This must be enforced by architecture, not policy documents. Platform failures are visible. Customers experience outages, data leaks, incorrect results. Unlike internal incidents, these failures, they damage trust quickly, spread through word of mouth, and they are difficult to explain away. So, strong platform security is a customer-facing feature. So how this mitigates earlier threat scenarios? Platform controls mitigate generative circuit abuse, multi-tenant inference risks, data exfiltration, export compliance failures, and denial of service attacks. They tie together all previous control domains. Many vendors still believe our users are researchers, they are not attackers. History shows misuse is often accidental. Incentives, they change, and trust boundaries, they erode over time. Security must assume good intent, but imperfect behavior. Well-designed platform security, it simplifies overboarding, it reduces friction with enterprise customers, and it enables broader collaboration safely. It is not a blocker, it is a growth accelerator. At this point of the series, we've already secured systems, data, models, hardware, and even platforms now. So the next video, it addresses a domain that cuts across all of them: export compliance and regulatory enforcement as an engineering problem. That's where we go next. If you work on AI, security, or law and want to understand what actually gets you sued and what should change, you are in the right place. Subscribe to my channel. This channel analyzes AI security legal risk, AI liability in practice, and AI governance compliance risk. We look at how AI system design, architecture, and runtime controls, they create legal risk in AI systems, AI model vulnerabilities and compliance failures, AI runtime controls and legal exposure, and how AI tooling risk translates to law for developers, security engineers, and governance teams. At many organizations, you would agree with me, export compliance lives in a binder. It is documented by legal, acknowledged in onboarding training, and forgotten in daily engineering work. That approach does not survive AI for quantum systems. In this domain, export compliance is not a legal afterthought. It is a system property. If compliance is not enforced technically, it will be violated accidentally. Export regulations were written for a world of physical goods, schematics, and clearly labeled technical documents. AI for quantum systems, it breaks those assumptions. Sensitive technical capability now lives in telemetry, trained model weights, calibration outputs, configuration files, and inference pipelines. You cannot rely on humans to recognize all of this correctly. Compliance must be embedded in the system itself. I'm Nupur Mitra, a legal and governance risk translator for AI systems. On my channel, The AI Law, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, risk issues, and the future of jurisprudence. The goal of export compliance controls is to ensure that 1. Controlled technical information is identified. 2. Access is restricted by nationality and jurisdiction. Processing occurs in approved locations. And 4. Violations are prevented by default. Compliance should fail closed, not open. Control 1. Export compliance, it starts with classification, but not at a document level. Quantum vendors must classify datasets, model artifacts, firmware, performance metrics, control techniques. Classification must be granular, reviewed periodically, and integrated into metadata systems. If an asset is not classified, it cannot be governed. Control 2. Export compliance, it depends on who can access what. So IAM systems must be able to distinguish user nationality or residency, must be able to enforce access restrictions automatically, and log and audit access decisions. So this requires coordination between HR systems, identity providers, and access control policies. Manual enforcement does not scale. Control 3. Export compliance is violated not only by people, but by infrastructure. So, controls must ensure data is stored only in approved regions. Compute jobs, they are run only where allowed. Backups and replicas, they follow the same rules. This must be enforced at the infrastructure layer. If a cloud region is not approved, the system should not deploy there. Control 4. Collaboration is inevitable in quantum development. So controls, it should require explicit approval for cross-border data sharing, review of assets involved, and time-bound access. So this turns collaboration from an ad hoc activity into a governed process. Speed comes from clarity, not from the absence of controls. Control 5. Export compliance, it requires knowing what moved, where it went, who accessed it, and when. So tracking must cover data exports, model downloads, training jobs, and derived artifacts. Without tracking, you cannot demonstrate compliance. Control 6. The most important control is this. The system should prevent violations automatically. For example, blocking access to controlled datasets for unauthorized users, preventing training jobs in unapproved regions, denying export of controlled model artifacts. So, humans should not be the last line of defense. So, why intent is irrelevant? A critical legal point here. Export violations, they do not require malicious intent. I didn't know is not a defense. This is why technical enforcement matters so much. It protects the organization from honest mistakes. Strong export controls, they enable international collaboration safely, reassure government and enterprise customers. They reduce legal uncertainty and they support due diligence for funding or acquisition. Poor compliance can halt operations, scare off investors, or trigger regulatory action. In practice, the opposite happens. Clear enforced rules, they reduce ambiguity, they speed up approvals, they prevent last-minute shutdowns. Engineers move faster when boundaries are explicit. Export compliance controls mitigate deemed export violations, accidental leakage of sensitive telemetry, model access of unauthorized nationals, and cross-border misuse of AI capabilities. They also strengthen your overall security posture. Export compliance is not separate from security. It affects system architecture, it determines access boundaries, it influences data flows. So, security teams must own this jointly with legal. So at this point, we've covered 6 major control domains: data governance, ML governance, supply chain security, hardware integrity, platform security, and now also export compliance. So the final domain, the next episode, it will focus on something often overlooked: customer assurance, auditability, and proving that all of this actually works. That's the focus of my next episode in the series. If you work on AI, security, or law and want to understand what actually gets you sued and what should change, you're in the right place. Subscribe to my channel. This channel analyzes AI security legal risk, AI liability in practice, and AI governance compliance risk. We look at how AI system design, architecture, and runtime controls, they create legal risk in AI systems, AI model vulnerabilities and compliance failures, AI runtime controls and legal exposure, and how AI tooling risk translates to law for developers, security engineers, and governance teams. Up to this point, we've designed a very strong security and compliance posture. But here is the uncomfortable truth. Controls that cannot be demonstrated do not exist in the eyes of customers, regulators, or even the courts. So this episode is about the difference between having controls and being able to prove you had them when it mattered. In quantum technology, where customers cannot independently verify correctness, proof it becomes the product. In most IT systems, customers can test availability. They can measure latency. They can verify correctness independently. But quantum customers cannot do that. They must trust your hardware, your models, your decoders, your control loops. That trust is fragile. It is earned not just through promises, but through evidence. I'm Nupur Mitra, a legal and governance risk translator for AI systems. On my channel, The AI Law, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, rights issues, and the future of jurisprudence. The goal of customer assurance and auditability is to ensure that every critical action is traceable, every system decision is explainable, every incident is reconstructible, and every control can be demonstrated on demand. This is not about paperwork, it's about operational truth. Control 1. For AI for quantum systems, provenance is everything. You must be able to answer which data trained this model, which model influenced this control decision, which firmware version ran this job, which configuration produced this result. Lineage must span data, model, deployment, execution, output. Without lineage, you cannot investigate or defend outcomes. Control 2. Audit logs should be tamper evident, time synchronized, and centrally accessible. So they must cover data access, model deployment, firmware updates, job execution, user actions. Logs are not just for security, they are legal evidence. Control 3. Customers will ask, how do you isolate tenants? How do you prevent model tampering? How do you ensure correctness? How do you handle export compliance? So you should have clear security documentation, architectural diagrams, and written assurances that match reality. Overpromising is dangerous and under-explaining is suspicious. Control 4. Your incident response plan, it must account for silent correctness and degradation, ML model compromise, firmware integrity issues, export compliance incidents. This is not the same as a traditional data breach. Plans must answer, how do we detect? How do we stop harm? How do we notify customers? And how do we preserve evidence? Unprepared responses often cause more damage than the incident itself. Control 5. As the industry matures, customers will increasingly expect SOC-style reports, third-party security reviews, or formal attestations. Preparing for this early, it reduces future friction, surfaces gaps proactively, and builds market credibility, which you want. So you don't need perfection, but you need seriousness. Control 6. Auditability, it also depends on people. Every control must have an owner, a review cadence, and escalation paths. Everyone owns security often means no one does. So clear ownership makes controls real. Many teams fear that logs and audits, they create liability. But in reality, lack of evidence, that is far more damaging. Transparency enables faster resolution, and good records, they demonstrate diligence. Courts and regulators, they punish negligence, not good faith efforts. So, auditability helps you detect reverse engineering attempts, identify model substitution, and prove decoder integrity, and also demonstrate export compliance and respond credibly to customer concerns. So it is the connective tissue across all domains. In quantum markets, technical differentiation is hard to evaluate. Security maturity is not. Vendors who can say, here's how we know our system behaved correctly, will win trust, especially with enterprise and government customers. Retrofitting auditability is expensive and painful. Designing for it early is cheaper, cleaner, and less disruptive. Auditability should be a design requirement, not a retrofit. So now we've walked through the threat landscape, 7 concrete control domains, and how to prove those controls matter. The final episode next, it will bring this together into an actionable summary and a concrete next steps plan. And that's where we'll conclude. If you work on AI, security, or law and want to understand what actually gets you sued and what should change, you are in the right place. Subscribe to my channel. This channel analyzes AI security legal risk, AI liability in practice, and AI governance compliance risk. We look at how AI system design, architecture, and runtime controls, they create legal risk in AI systems, AI model vulnerabilities and compliance failures, AI runtime controls and legal exposure, and how AI tooling risk translates to law for developers, security engineers, and governance teams. I know at this point in the presentation, a reasonable reaction is, this all makes sense, but what do we actually do? This episode, it exists to answer that question directly. What you're looking at here is not a multi-year transformation program. It is minimal, credible 90-day plan that materially reduces risk without slowing development. So the emphasis is going to be on leverage, sequencing, and actions that compound. This plan is deliberately designed to work for startups and mature vendors alike, run alongside active R&D, and create visible progress quickly. It focuses on control primitives. Once these exist, everything else becomes easier. So, I'm Nupur Mitra, you already know me by now, a legal and governance risk translator for AI systems. On the AI Law, my channel, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, rights issues, and the future of jurisprudence. So in month 1, establish visibility and integrity. 1. The single most important month 1 activity is this. Stop treating telemetry like generic logs. So what are the actions for that? Identify raw telemetry, calibration traces, and experiment logs. Classify them explicitly. For example, restricted device telemetry. Restrict access to a minimal set of roles. Separate raw telemetry from derived datasets. I'm sure you must be wondering why this comes first. It immediately reduces reverse engineering risk. It prevents accidental export violations. It clarifies ownership and responsibility. This is low cost and high impact. 2. So next, establish basic ML artifact control. For that, what are the actions? You will create a central model registry. Require models to be versioned and immutable. Introduce cryptographic signing for approved models. Enforce verification at load or deployment time. And now, you must be thinking, why this matters early? It prevents silent model substitution. It creates accountability for machine learning changes. It lays the foundation for auditability. You don't need a perfect ML governance system, just a real one. 3. Finally, for month 1, address supply chain visibility. Actions: generate a basic SBOM for control software, ML pipelines, decoder runtimes. Pin critical dependencies. Identify which components are high impact. This does not require deep audits yet. It requires knowing what you run. Month 2. Now that controls exist, month 2 focuses on detection. Actions: define baseline performance and fidelity metrics. Monitor for statistically significant drift. Track model output distributions over time. Alert on anomalies, not single failures. So why this matters? Yes, you're right to think that. Most AI for quantum failures are silent. Drift is often the first observable symptom. Early detection, it prevents long-lived corruption. So, this is your early warning system. So next, harden the lowest trust layer, and actions would be identify firmware and FPGA bit streams in use. Introduce signing for approved images. Enforce verification before execution where feasible. And log updates and deployments. So why this is month 2 work? It depends on supply chain clarity from month 1. It materially reduces silent correctness risk. It protects against both mistakes and attacks. You don't need perfect attestation. Progress counts. Now formalize export compliance as an engineering concern. So what are the actions? Run a joint workshop, engineering plus legal. Classify datasets, models, and artifacts. Map classifications to IAM rules. Enforce region-aware and nationality-aware access. And why is this essential? Good question. Export violations are catastrophic, not incremental. Enforcement must be technical, not policy-based. Early clarity prevents future shutdowns. So this protects the company as much as the technology. Now let's go to month 3. Month 3 is about testing reality. What are the actions? Simulate poisoned calibration data. Attempt a model swap without proper signing. Observe detection, response, and recovery. The goal is not to win. The goal is to learn where assumptions break. So next, formalize response. Actions: write a runbook for ML model compromise, control loop degradation, decoder integrity failure, define the rules, escalation paths, and evidence collection. Practice once at least as a tabletop. Trust me, preparedness here is a massive risk reducer. Turn internal controls into external confidence. Actions: document security architecture, summarize control domains, prepare answers to customer security questions. Align with SOC 2 style expectations even if uncertified. So what happens here? This accelerates sales, partnerships, and also trust. That's important. In 90 days, this plan delivers real risk reduction, defensible governance, and customer visible maturity. Not perfection, credibility. So, if you work on AI security or law and want to understand what actually gets you sued and what could change or what should change, you're in the right place. So subscribe to my channel and there'll be lots and lots of more series to come. If you work on AI, security or law and want to understand what actually gets you sued and what should change, you are in the right place. Subscribe to my channel.
This channel analyzes AI security legal risk, AI liability in practice, and AI governance compliance risk. We look at how AI system design, architecture, and runtime controls, they create legal risk in AI systems, AI model vulnerabilities and compliance failures, AI runtime controls and legal exposure, and how AI tooling risk translates to law for developers, security engineers, and governance teams.
So this is an add-on to my AI for Quantum series. Red team scenarios, tabletop, and technical exercises. So why red teaming is non-optional? This episode exists for two reasons. One, because you all wanted it. You all asked for it. And two, controls you've never tested do not exist. AI for quantum systems, they fail in subtle ways. Red teaming is how you surface those failures safely. So let's understand scenario 1. Poison calibration data to degrade fidelity by 2%. Objective: reduce system fidelity slightly without triggering alarms. And why this matters? A 2% drop may be commercially or scientifically significant, but it looks like normal noise. And what are you testing? Drift detection, baseline quality metrics, alert thresholds. I'm Nupur Mitra, a legal and governance risk translator for AI systems. You all already know me by now. I'm a lawyer by profession. On the AI law in this channel, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, rights issues, and the future of jurisprudence. So now let's understand scenario 2. Swap decoder weights to bias-specific circuits. Objective: introduce biased decoding for selected patterns. And why does this matter? Targets: correctness, not availability. Extremely hard to detect without integrity controls. And what are you testing here? Model signing, deployment gates, audit logs. Scenario 3. Exfiltrate telemetry via support bundle. Objective: extract sensitive telemetry using legitimate workflows. And why this matters? Most real leaks, they happen through support and debugging, not through hacking. So what are you testing here? Data minimization, access logging, export awareness. Scenario 4. Introduce malicious dependency in ML runtime. Objective: alter behavior via a compromised dependency. Why this matters? Supply chain attacks are common. Machine learning ML stacks, they have deep dependency trees. And what are you testing? SBOM accuracy, dependency pinning, vulnerability response. Scenario 5. Cross-border dataset exposure via cloud misconfiguration. Objective: trigger a deemed export without human intent. Why this matters? This is how real export violations happen. What are you testing? Region enforcement, IAM correctness, logging and detection. Red team success is not preventing the attack. It is detection time, containment effectiveness, quality of evidence, clarity of customer communication. Those are what regulators and customers care about. So now let's analyze the key takeaways here. 1. The real security threat is dual use capability. The threat is not quantum supremacy or futuristic crypto analysis. The threat is ML in the loop capability, creating new attack surfaces today. That's already happening. 2. Data, models, and accelerators are crown jewels, not just code. Telemetry, model weights, control outputs, decoders, firmware. These assets, they define competitive advantage and risk exposure. Protect them accordingly. 3. Export compliance must be engineering enforced. Policy alone will fail. Compliance must be embedded in IAM, enforced in infrastructure, logged automatically. This protects the company as much as the country. Takeaway 4. Evidence is as important as controls. Logs, lineage, signing, and SBOMs, they're not bureaucracy. They're customer trust, legal defensibility, and operational clarity. If you can't prove it, you don't have it. So, security maturity in quantum systems is not optional. It is a prerequisite for scale, a differentiator in the market, and a shield against existential risk. If you work on AI, security, or law and want to understand what actually gets you sued and what should change, you are in the right place. Subscribe to my channel. This channel analyzes AI security legal risk, AI liability in practice, and AI governance compliance risk. We look at how AI system design, architecture, and runtime controls, they create legal risk in AI systems, AI model vulnerabilities and compliance failures, AI runtime controls and legal exposure, and how AI tooling risk translates to law for developers, security engineers, and governance teams. This episode exists for 2 reasons. 1, because you all wanted it, you all asked for it, and 2, controls you've never tested do not exist. AI for quantum systems, they fail in subtle ways. Red teaming is how you surface those failures safely. Quantum AI patent filings are surging, and that simple fact might decide who owns the future. If patents are rising faster than breakthroughs, someone's already placing claims to tomorrow's power. 2024 saw record high AI patent publications at the European Patent Office (EPO), and quantum AI QAI filings, they grew nearly in lockstep with AI. That's not coincidence, that's a legal land grab for the next tech frontier. So welcome to the AI Law Talk, where I break down AI developments through a techno-legal and policy lens. Subscribe, share the news you see, and I'll unpack what it really means. AI patent publications at the EPO hit at all-time high in 2024. Importantly, quantum AI patent filings, they reportedly grew in line with overall AI growth, indicating that innovation merging quantum computing and AI is not just speculative. Actors are formally staking claims. Geographic shifts. While the US and South Korea, they lead per capita in classical AI filings at the EPO, Japan has surged ahead in per capita QAI filings, even surpassing the US. But there's a catch. The report notes that QAI applications, they face a roughly 4% lower allowance rate compared to classical AI applications. That suggests higher scrutiny or technical complexity likely to patentability criteria, like the need to solve a technical problem under EPO rules. Many QAI filings are for optimization problems. Domains where quantum computing may be especially useful, like supply chain design, logistics, scheduling. However, some of these use cases, they risk being classified as non-technical under EPO practice, which can jeopardize patentability.
So the bottom line from the data, quantum AI isn't just research anymore. It's being positioned for commercialization, corporate control, and legal ownership. When investors start patenting what doesn't yet exist, algorithms, hybrid quantum AI workflows, they're not betting on future tech. They're banking on future control. So let's understand the techno-legal and policy implications here. Patents as power, not just innovation. Patents don't just reflect invention, they reflect ownership of possibility. In fields like quantum AI, where the hardware and full realization may lag, patents function as preemptive enclosures. Whoever holds them controls who gets to build next. Gatekeeping and innovation barriers. Given the lower allowance rate for QAI and the EPO's strict requirement for technical character, many QAI innovations, especially in optimization, logistics, business method adjacent use cases, may be denied. That means innovators will need high-quality drafting and technical grounding to get through. Companies that succeed will hold a strategic advantage. Those who don't may be locked out. Dual use and national security risks. Quantum computing and AI has implications far beyond commercial software, from cryptography to supply chain logistics to defense adjacent optimization. As patents accumulate, these may shape not just businesses, but national security posture. That raises the stakes for regulators. Export controls, licensing restrictions, cross-border IP conflict, and oversight regimes, they may become necessary. Innovation versus monopoly, the research risk. If foundation quantum AI methods are locked behind broad patents, academic research and smaller innovators may be prevented from experimenting, adapting, or even building derivative tools. Public good innovation, from health to climate to open science, they may suffer. Quantum AI patents today might decide who gets to develop tomorrow's critical infrastructure before the infrastructure even exists. So let's understand the sector-by-sector impact and what to watch. In finance and optimization, quantum AI optimization patents could transform trading algorithms, risk analysis, supply chain optimization, logistics and global financial infrastructure. Whoever owns the IP could control future capital flows. Pharmaceuticals, materials, and energy. Quantum simulation plus AI could accelerate drug discovery, materials design, for example, batteries, catalysts, superconductors. Climate modeling. If patent fences go up early, the resulting breakthroughs, even in public health or clean energy, could be captured by a few actors. Cybersecurity and cryptography. Quantum plus AI is equal to potential to break classical encryption, but also to create new cryptographic protocols. Patents in this space could define who controls future cybersecurity infrastructure and who profits from licensing or compliance. Geopolitics and industrial policy. With per capita QAI patent surges in places like Japan and major filings globally, quantum AI might reshape economic competition. Countries may start treating quantum AI as a strategic asset, leading to export controls, national security regulations, and international IP battles. This isn't about one company winning at tech. It's about who writes the rules, and patents are the legal rulebook for the next technological era. So now is the real question: what this means for public interest, regulation, and policy. Access versus ownership. If QAI becomes proprietary, essential innovations, for example, clean energy or public health, risk being paywalled, licensed, or siloed, undermining open access and social benefit. Need for regulatory foresight. Regulators and policymakers, they must anticipate quantum AI's dual-use potential. Patent law alone may not be enough. We may need export controls, classification regimes, or even licensing requirements for critical applications. Patent landscape transparency. Because the field is nascent and complex, stakeholders like governments, public interest organizations, and even researchers, they must monitor who gets QAI patents in what jurisdictions and under what claims to avoid monopolies and preserve competition. Support for open or commons innovation to ensure that quantum AI benefits aren't hoarded by a few actors. Quantum AI patents won't just shape who builds technology, they'll also shape who benefits from it and who gets left behind. So the final takeaway, the surge in quantum AI patent filings is more than a pattern. It's a foundation being laid. The next generation of AI-powered quantum-driven tech will emerge in a legal landscape already carved out by those who first filed it. If we want an AI future that centers equity, access, shared progress, we need to recognize this early. Because when the technology is new, the patents have more power than the tech itself. If you want clear, honest, legally grounded takes on what's really happening behind the AI hype, subscribe to the AI Law. Hit share to spread the signal, and I'll keep analyzing the developments that might shape your rights, your work, and society's future.